Okay, is it working now? All right, so yesterday I tried to give you an overview of sort of the different machine learning tasks, and then tried to explain the principle behind how you write down a loss function for training your machine learning algorithm, and then started to introduce neural networks. And so that's where we're going to start today. And the plan of today is to get through the basics of what a neural network is, the algorithm of how we train it, something called gradient descent. And then we should have everything we need to tackle our first working example, our first physics example, which will be binary classification using neural networks. And specifically, we'll look at top tagging, so identifying boosted top quarks out of the QCD background. OK, so that's the plan for today. All right, so let's start with the simplest neural network. It goes by many names. Some people will call it a feed-forward neural network or a dense neural network, sometimes abbreviated DNN. You'll sometimes see this is a bit antiquated, multi-layer perceptron, or MLP. So it has many names. And it's the thing which, and another one is fully connected. OK, and yeah, so it's probably the picture you've seen before, but you usually represent it with a series of dots or circles that are called nodes. And you start with what's called the input layer. So what I'm going to do is basically graphically represent a recursive function that's going to be our family of fitting functions. OK, so this is the input layer. Call it to represent x. OK, so remember we had the data. The data were xi living in Rd, right? So there are d of these nodes that we feed the data to as the input layer. Okay? And then the DNN has a number of what are called hidden layers, which have the same form. Okay, so each of these are called hidden layers, and I'll denote them with x1, x2, x3, ... And then finally, there will be an output layer. Let's give this a name. We'll say that this is z, okay? And it's our function that we had defined last lecture. Okay, so the idea is that we start here and we propagate the information or the input layer data through this structure. Okay, and the way we do that is this is called a fully connected neural network. So every node connects to every other node, okay, et cetera. And each of these connections indicates a parameter of the neural network. Yeah. Each of these connections indicates a parameter of the neural network, one of these thetas that we can then fit for. OK, and so the structure is recursive, and I guess it's biologically inspired. And so let me just show you, first of all, how you get the first layer. Oh, sorry, so these are called hidden layers. And this is called the output layer. So let me just show you how you get the first hidden layer starting from the input. In case all this lines and things look overly complicated, all we're doing here really is matrix multiplication. OK, so basically all the connections there correspond to a big matrix, call it W, the weight matrix, which just acts on the input layer as if it were a column vector. Okay? So just think of these as column vectors that might live in different dimensional spaces. I mean, let's say this is d-dimensional, and this has its own dimension, which we're going to choose at some point. Okay, so this is a big matrix which multiplies this column vector. Okay, and we also find it useful to add an additional column vector to this. So these are called the biases. Okay, so these are weights, and these are biases. And these are the trainable parameters of this neural network. They're what make up the theta. Okay, so actually, if I just did this, and I repeated this structure all the way through, I would just have matrix multiplication all the way through, and this would be a linear function of the inputs, right? So that's clearly not enough to get us the universal approximation theorem to fit any data we want. So what people realized is that we have to introduce a source of nonlinearity to this. And so what people do in the simple DNN is to put what's called an activation function here. Okay, so this is called the activation function. Okay, and it's a source of nonlinearity. And I think in the early days, people took activation functions to be, so examples of activation function So one of the original ones, I think, which was, again, inspired by, I guess, the activations of neurons, is called the sigmoid activation, which looks like this. If you plot it, x can go from -infinity to infinity, and the sigmoid goes from 0 to 1. Okay, so this is called the sigmoid activation. Another one, which is closely related, is the tanh, which is basically the same thing as the sigmoid, except it goes from -1 to -1 to 1. Okay, so this is the tanh activation. And these were widely used, I think, until the modern times, when people realized that they were hurting the training of neural networks because the information you get from the activation kind of saturates when the inputs are too large or too small. Okay, so in other words, the activation kind of saturates at 1 or 0 or 1 and -1, and in particular, then the derivative of the activation goes to 0. So we don't get any more information from the activation. So these led to something called the vanishing gradient problem, and were part of the technical part of the reason why neural networks weren't very successful until relatively recently. Yes, question.
Since these two activation functions essentially have the same shape, how could they give you different outputs?
Well, yeah, so good. So yeah, I mean, they just have a different range. But yeah, they're essentially the same thing. Yeah, yeah. The only place you might, basically, yeah, if you use one of these in the inner layers of the neural network, it could probably compensate for the difference. And the only place you would see a difference is at the very end. Yeah, so good question. Yep, is there another question? Okay, so good. So in the modern era, this is sort of the engineering aspect of this subject. People realized that a much better activation function to use is the following weird thing. So what this is if you graph it, it's just 0 if x is less than 0. Otherwise, it's just x. And so this does have vanishing gradients if x is less than 0, but it doesn't have any vanishing gradients if x is greater than 0. And this is called the rectified linear unit activation. Yes, question?
Why don't we just use like absolute value of x or something?
Absolute value of x. Yeah, well, I guess, yeah, you could. So that would be like this.
Yeah.
Yeah, so you could. I haven't seen that. It's not very popular. I think there must be some advantage to, well, the short answer is I don't have a good answer. A lot of this is just voodoo, but seriously, but it's empirical. So maybe absolute value works just fine. I don't know. I've never tried. But I think there might be some advantage to shutting off the activation, allowing the activation to shut off. Like then basically that'll sort of tell you that think of this as, I guess, like, if it's biologically inspired, right, there are some pathways through this that through the training will be emphasized and other pathways which will be de-emphasized. They'll be more or less relevant to accomplishing the objective. And so having the ability to shut off the activation probably contributes to that. But no, it'd be interesting to try. The absolute value, maybe. There is something called leaky ReLU where you give this a small slope, but usually people take that to be very small, like 1% slope, whereas what you're suggesting would be order 1. So yeah. Okay. Good. So this turns out to be much better for training, in particular for training deep networks. Yes.
Is the absolute value less favored in part because it's non-monotonic?
Maybe. Again, I don't want to say, yeah. There's really very few theorems in this subject. Yeah.
In this way, we never have a negative output.
Sorry, what?
In this way, we never have a negative output.
In this way, we never have a negative output. Yeah. Although the sign of this thing probably isn't that important because in the next layer, you're going to multiply it by some weights and then add a bias to it, et cetera, et cetera. So any overall shift in this probably could be compensated for by, yeah. Okay, good. So anyway, so I'm just telling you that, in the modern era, people tend to just pick ReLU and go with it, or some cousin of that. And good. Okay. So that gets us to the first layer. Oh, and in case you're wondering, how does any of these functions, these are scalar functions, right? How do any of them act on a column vector, right? So you might be wondering that. How do any of these activation functions act on a column vector? And so that's where this becomes, I think, kind of computer science-y. These act element-wise. Okay, so it's not a very intuitive thing, I think, from a physics or math point of view. But yeah, so the activation functions act on each component of this column vector separately. Okay, yeah?
Is there a reason that all of the activation functions you draw are topically increasing?
I think the general principle is you want the information to be able to shut off. So yeah. So yeah.
I think that it's because of the entropy. So when we have these neural networks, we are essentially looking at entropy minimization. And so having a positive x in the activation function favors the activation function, and having a negative value reduces the entropy, so it disfavors, which is why all of them are increasing. And so which is why negative values are kind of disfavored and positive values are favored. So we have entropy going in one direction and not the other way.
Maybe. Yes, maybe. Okay, so all these questions are good. I think they're touching on, there is like a whole nother branch of ML, the theoretical or the theory of ML, where I think people do study these questions. But they, again, because it's a very empirical subject, they study them, the way they study them is using toy models. For instance, people will take these feed-forward neural networks and specialize to infinitely wide neural networks. And that's a weird thing to do. But if you take them, turns out if you take them infinitely wide, they become essentially like free field theories. And in that limit, you can actually derive that ReLU has some special properties. So I'm not an expert on that, but I have heard about it. And if you like, there's a whole book on that on the archive that goes through a derivation of why ReLU is special. But in there, I'm not sure I saw any sort of intuition for why it has to be monotonically increasing or anything like that. Yeah. Yes? Oh, absolutely not. Yeah, so that's a choice people make. And just for simplicity, we typically pick the same activation for all the layers up until the last one. But you don't have to. Yeah. OK, good. Good, so that brings me, that's a good question to bring me to the subsequent layers. So I've shown how to get from input layer to the first layer. So now let's do the next one. Well, let's just do the nth layer. It's a recursive or self-similar structure. The nth layer is the same idea and depends on the n-1th layer and a new set of weights and biases, and a new activation function, which could, in principle, as you asked, be different. OK. And finally, the output layer. Oh, yeah. So let's say there are L hidden layers. OK. Then the last output layer is just given by this. OK, and so usually we pick A1 to AL is ReLU for simplicity. And then the last layer is special. Just a second. The last layer is special because that's the one that we're going to want to do whatever it is we want to do. For instance, for binary classification, we want this to function as a probability, right? That's what we discussed last time. So if it's a probability, which one of these, of the three I've mentioned, should be the appropriate one? Probability should be between 0 and 1, right? So we always use the sigmoid activation for the last layer. So yeah, this one, AL plus 1, determined by the task, for example, sigmoid for classification, for binary, well, yeah, for classification. OK, yes, you had a question?
Yeah, it's good. Thanks.
OK, good. All right, so the collection of all the W's and B's of every layer, they make up the parameters of the neural network. OK, and they're the things that we're going to fit. And so you can see very quickly that how many parameters we have, it depends on how big our input layer is, how big our hidden layers are, how many hidden layers we have, et cetera, right? And things go like n squared. So you can quickly get to a large number of parameters. Yeah. So for example, let's do an example. Let's say we have 100. So D is equal to 100. So 100 input features. Let's say we have 5 hidden layers with 100 nodes each. And let's say we output to a single and output layer dimension equals 1. Okay, so we output to a single node. That could be something we do for binary classification. So in that case, between each layer, we have 100 squared connections, right? 10 to the 4. And we have 5 such layers. So that's of order 50,000 parameters. And we have the biases as well. So this is of order 50,000 parameters. And this would be considered sort of a small DNN. Okay? And so you can easily get to say, 1 million parameters. And so it's kind of a miracle of modern computer technology that we can minimize such functions. Yeah. Okay. Good. What else? Oh, yeah. So another comment I want to make here is something called hyperparameters. Okay, so when we talk about these neural networks or machine learning algorithms in general, we have to distinguish between what are called, these are called trainable parameters. These are parameters that are going to be adjusted during our optimization of the loss function, okay, in a way using methods that I haven't, that I will tell you about in a minute. So these are the trainable parameters. And then there are additional parameters that define the neural network architecture and also how we train it that don't get adjusted during the training. Okay, and these are called hyperparameters. So examples of hyperparameters here might be L, the number of hidden layers, right? Let's say each layer, I probably should have defined it here, but let's say each layer has dimension D1, D2, D3. So all the dimensions of the hidden layers, D1, D2. These are all choices we can make in defining what's called the neural network architecture. Okay, so how we design this neural network is our choice, and the choice of design, it gets called the architecture of the neural network. Okay, the choice, some hyperparameters are not just integers, some are discrete choices. So the choice of activation is in some sense a discrete hyperparameter, right? If we did something like I said, leaky ReLU that has a choice for the slope here, that's another hyperparameter. So there's not just one universal neural network architecture, but in general, this is so if you really want to get the best possible result, this is something you have to do after you optimize your neural network. You have to then scan over these hyperparameters and see if some hyperparameters are better than others. Yes?
I'm still a little bit confused about what the network is actually doing. So we have some data in the input layer. It gets passed into these hidden layers whose values are defined by the activation function that we specify. And then we have these weights and biases that it's supposed to fit, but I don't understand. At what point in this process does it do that? How does it do that?
Okay, I haven't told you yet how we fit these things, so that's going to come next. But yeah, for a given choice of weights and biases, for a given choice of these trainable parameters, what this is just a complicated way of describing a series of matrix multiplications and then nonlinear activations, matrix multiplications, nonlinear activations, et cetera, until the end. So it's a feed-forward neural network. You feed the information in here, you do the matrix multiplication and activations all the way through, and you get some numbers out. That's what the function is doing. Yeah. And then the last step of all this is to explain how we minimize the loss function to determine the best fit values for these W's and B's. Does that answer your question? Yeah. Okay. Sure.
So the hidden layers.
Mm-hmm.
So why not just go straight from the input layer to the output layer? It seems like these hidden layers, the purpose of them is to just add more parameters that we can fit.
Yes.
Is that?
That's it.
That's all there is to it?
Yeah, so I could say a little bit more. So if you look at the theory of ML, the very early theory, of neural networks, you'll see that there's something called the universal approximation theorem, which the original form it was proved in says, if I have a single layer, but I make it infinitely wide, then it can fit any function. Okay, and then people subsequently proved that, I think, that if you take not just a single layer, but an infinitely deep neural network of finite width, it can also fit any function. So the general DNN that we're writing down is somewhere between those two limits. And the idea is that the deeper I make it or the wider I make it, the more expressive it becomes. Does that answer your question? Yeah, our goal is to be able to fit or be like infinitely expressive. We can fit any function or any data. Yeah. Good. OK, so I think there's one more thing I wanted to say, which is the reason. So you may have heard of GPUs before. They're the graphics cards that power your laptops or your gaming systems or computers. And it turns out people realized at some point, not too long ago, that GPUs are ideal for training neural networks, training and evaluating neural networks. And the reason is that GPUs are designed for what's called vector or matrix algebra. So GPUs are just very specialized chips that can multiply matrices very fast. And you see, that's what goes into a neural network. And I think it's really fascinating. These things developed completely independently, and it took some smart person to realize, hey, there's this hardware that was developed so people could do like first-person shooter games, and it's perfect for training neural networks. So it's a happy accident, I think, of technology. Yes?
By better, do you mean faster, or is there something deeper there?
Yeah, faster.
Okay, gotcha.
Really fast, yeah. Thousands of times, or yeah, much faster. So yeah, so it's a happy accident of engineering technology that GPUs are ideal for this. OK, good. So now we can talk about training. OK, so now how do we fit when the dimension of theta could be like 1 million? Yeah? So what algorithms can we use to fit such functions with so many parameters? So unfortunately, I don't have time to go into a lot of detail about this. So I'm just going to focus on the rough idea and some of the concepts. OK? And so if you think back to if you ever fit anything in your life or minimized anything before, maybe in calculus class, there's one method which is really nice, but unfortunately doesn't work in this context, namely the Newton method. Right? So idea one, which doesn't work, is something like the Newton method. We start with maybe an initial guess, and we imagine perturbing around it. Right? So let this be theta. Okay? And let's expand around our, so our loss function is a function of theta. Let's expand around our initial guess. And we're going to get a constant term, and then a, here, let me write it like this. We're going to get a linear term, and then we're going to get a second order term, right? And actually, let me just write this out as if it was a one-dimensional problem. Hopefully, you can generalize it to an n-dimensional problem in your head, just so I don't get too bogged down with the notation. OK, and so what should we do to get the next guess for the better fit value? We should just take this quadratic approximation and hope it's good, right? And then take the second derivative. Take the first derivative, set it to 0. OK, so this is, I think this is called the Newton method, or something like it. So we approximate the function we want to minimize with its Taylor series, truncated to second order. And then so this is approximately this. And so this is, set this to 0. This is approximately dl d theta plus delta theta. Right? So we set that to 0, and we get our next guess for the best fit value is just just this. Okay, so this seems like a really nice thing to do. Why does this not work in the case of large neural networks? Oh, I can calculate the derivative. Yeah, I could do that. So that's not the reason.
The Taylor series approximation is bad.
No, the Taylor series approximation would probably be decent. Much better than the alternative I'm going to show you, which is totally crazy.
Computing the matrix inverse?
That's right. So, okay. So if I had written it out with all the indices, this here would actually be a n by n dimensional matrix where n could be 1,000,000 dimensions, right? So, which is I think called the Hessian, right? So inverting that is in general intractable. I think it goes like the cube of the dimensions. So it's just not possible to invert such a large matrix. Okay, so this is a 1,000,000 by 1,000,000 dimensional matrix inverse, and so this is not tractable in practice. Okay, so the Newton method, which is a second order method, okay, it goes to second order, is in general intractable for the large neural network type things that we want to optimize. Question?
Sorry if this is a little bit jumping ahead, but
Yeah.
Adam basically trying to do the same thing, except it tries to estimate the inverse of the.
Yeah, this is jumping ahead. I'm going to mention Atom in a couple steps. Yeah. I would say maybe there's a sense in which that's true, but I would say it differently. So, yeah, okay. Good, so instead of something like the Newton method, yes?
So if you have some kind of instance where this Hessian matrix is like a sparse matrix because you turn off a lot of these things, can you do this?
I've heard talks about that from like ML people. So yes, they try to play such games. I think in general, for general DNNs, this is not a sparse matrix. So yeah, so it doesn't have, as far as I know, it doesn't have very broad applicability. Yeah, but yeah, that's a good idea, I think. Okay, so good. So instead, idea 2 is to try something at first order. Okay, so idea 2 is to basically say, so instead, neural networks are optimized with first order methods. And it's kind of amazing that this works, but the idea is simply to say that although at first order, yeah, so what do we have information about? So if the function that we're trying to minimize looks like this, then at first order, we take the derivative, okay, and we know which direction do we want to go in. We want to go this way, right? So at least the derivative hopefully points roughly in the right direction. So I think that's the idea of the first order method. So you literally just do this. So you compute the first derivative of the loss. Okay, that gives you a direction in parameter space. And you say, I hope that direction is at least pointed roughly in the right direction. And I multiply it by, now I introduce another hyperparameter. This is called the learning rate. And the idea is I have to choose this learning rate to not be too big or too small so that the gradient, which is not a perfect estimator of where I want to go, doesn't, if I choose it too small, I'll take forever to go from here to here. If I choose it too large, then any small mistake I make could knock me way off course, and I may never converge. Okay, so that's the learning rate is another hyperparameter. Yeah, and so this is called gradient descent. And because it's far from perfect, we end up having to do this over and over and over again. Okay, we calculate these gradients, we update the weights, and so this is called the gradient update. We update the weights. And then that gets us to another place in parameter space, and we do it again and again and again, and we hope that we converge eventually on some decent answer. Yes?
It's surprising to me that a first order method with order a million parameters would perform better than like a second or third order method with much fewer parameters.
Yeah, interesting. I guess, yeah, the price you pay for not necessarily finding the global minimum here, I guess, is outweighed by the much improved expressivity of the function empirically. Yeah, that's definitely the case. Good. Okay, so this is called gradient descent, and this is not exactly what we do when we train neural networks. And the reason is that the loss function is in general not convex. Okay, so if only it were, right? But in general, it is very high dimensional and has many peaks and valleys. Okay, flat directions, all sorts of things. So if you just did this, what you would quickly realize is that it's very easy to get stuck at a local minimum. Okay, and we don't want to get stuck in a local minimum. We want to ideally find something approximating the global minimum. Okay, and so what people realized. I don't know at what point, but what people realize is actually it's advantageous to introduce some noise into this process. So so the gradient is a poor estimator already, but actually it's better to make it even poorer. Yeah, so making it noisier is actually better. So then we might get stuck here for a while, but with the right amount of noise, we could jump out. Okay, and there are statistical mechanics analogies to this that I'm not an expert on. But anyway, suffice to say that what we actually do is we figure out a way to make these gradients noisy, and then that actually improves the fitting, the outcomes, the convergence of these things. Okay, so, and there's actually a very simple way to make these noisy, which I guess I will write over here. Yes?
How likely is like super high dimensional space are you able to get like a local minimum as opposed to just a saddle point?
Good. So yeah, I think saddle points are generally not the problem. It's more like, do we get stuck in a very suboptimal local minimum? Yeah, I guess there's enough noise typically that I guess we don't worry about. I mean, to be perfectly honest, it's impossible to visualize or really get any intuition for a million-dimensional, a function on a million-dimensional space. So,
How would you imagine like if you're at a certain point, then like the second derivative would just like be there's a lot of choice or like a lot of dimensions that you can have, and it's kind of unlikely to me that they're all positive.
You mean that there exists a global minimum?
No. I mean like just if you start from somewhere and then you end up in the place where you're apparently stuck. And
you think it's unlikely that you could be stuck somewhere?
No. I think it's like unlikely if there doesn't exist a dimension in which you have, let's say, a very flat.
Very flat. Yeah. Again, this is something people study with toy models. Yeah.
No, I don't know. I'm just.
You can also see this empirically by like hyperparameter optimization. Like if you try to optimize the
Mm-hmm.
hyperparameters of your network, you'll often end up in like a minimum half the time or a third of the time where it's like much lower than the other minimum. So it's definitely like empirically true that it's pretty easy to get stuck in one of these minima.
Yeah. Okay.
Yeah. One thing people will do is after we settle on some hyperparameters that we think are good, we'll train the same network many times to get ensemble of predictions, and we'll see that the results generally scatter around. There's some law of large numbers happening here, so the results generally scatter around some typical value. So even though there's a landscape of local minima or values or anything, somehow the outcomes have like a statistical property to them. Yeah. Is there another question? Yeah.
Would the optimal amount of noise in some way be equal to sort of the depth of the global minimum?
Yeah, if we knew what that was.
Right.
Yeah. Right. Yeah, there would be like some optimal temperature or something where you could bounce out of the local minima but not out of the global one or something. Yeah, but we don't know what that is in general. So instead, people figured out what I think is a clever way to introduce noise into this problem and also to make it sort of more, a little bit faster to compute. So the L that I've been talking about up till now is a sum over all the data of whatever loss function that we are applying to each data point, right? And if you like, this is like the best estimator of the gradient, of the loss function that we're going to get, right? Because we use all the data. And so what people realize, and so it can be expensive to compute if I have 1 billion data instances, right? So people realize you could kill 2 birds with 1 stone. You could make the loss cheaper to compute, or the gradients of the loss cheaper to compute, and introduce noise into the problem. And you could do that by literally just taking, the extreme version of this is just, so if you like, I can think of this as n data times the average of this thing, right? And so instead of taking the average, I could get a noisier estimator for this thing just by taking, in one extreme, a single example. So instead, so if I take a single example, then I say that L of theta is approximately too many parentheses? Yeah. Okay. So that's an extreme example. So this is called, and this is, I guess, this is technically what people, well, this is called stochastic, or the most stochastic gradient descent, where you estimate the gradient using 1 data point at a time. Very noisy. Okay, so typically this is a little too noisy for most people's applications. Yes?
Sorry, I don't think I understand. How do you estimate the gradient?
Good. So the least noisy estimator of the gradient comes from averaging all the data together. Yeah? So just think of like each data point is giving you some information about the gradient, and I'm averaging them all out. That smooths out all the fluctuations. And I can get a very, very noisy estimator if I just take a single data point. And I make sure that so the idea is I would update the weights not using the full data set, but using a single data point. And then I update them again using the next data point, et cetera, et cetera, et cetera. So I kick the function, or kick the weights around with a lot of noise. And if I run through the entire data set, then in some sense I've used all the information that went into this, but I've like exposed it to a lot more noise. Yeah?
This just tells you what the loss function is, right? So I guess, like, do you calculate the gradient by varying its theta individually, or
By varying what?
like each theta individually? Like,
Yeah, no, so yeah, this is a vector of thetas, and this is like a gradient with respect to theta, if you like. So the update happens to all the thetas at once.
so I'm talking about how you actually calculate the gradient. You just like run algorithm with the specific set of numbers that you use.
Right, so yeah, so we start the algorithm usually with some random choice of thetas, and then we do this update, and we shift the thetas by delta theta, and then we do another update, shift them by another delta theta, et cetera, et cetera. Does that answer your question?
It's how you compute gradient of L.
Oh, I just differentiate this with respect to
You
theta.
have a function, and so that's the end of the calculation.
I know this function, sorry, okay, so I know this function, this is my neural network. Good, okay, sorry, I didn't understand your question, thanks. So I know this function, this is my neural network. Okay, I have to differentiate it with respect to all the weights, which is a little bit nasty, but that's what computers are for. Okay, and that's actually where this backpropagation algorithm comes in, which I'm not going to tell you about, but that's where use the chain rule many times to compute the derivatives of this with respect to theta. Now L, let's just be concrete, L could be the binary cross entropy loss that I defined last lecture. So L is also fully specified. So now everything is specified and I can compute the gradient. Does that answer your question? Great. Okay, good. So yeah, so this stochastic gradient descent with a single instance is too noisy usually. And so what we do instead is we say, let me average this over what's called a mini batch. So I just sum over a portion of the data. So maybe 100 data instances. Okay, and so what I really do is I take all my data and I chop it up into non-overlapping mini batches. Okay, so this is called batch gradient descent. And this is typically what everybody does, so we sometimes just call it gradient descent. Okay, so what we do is we chop up the data. Let's say I have n data total, and then I'll chop it up into equal size batches, and I'll compute the gradient on each batch, and then update the weights, and then cycle through. And then continue all the way through the data. Yes?
Why wouldn't you want to increase the batch size each time as you're sort of getting closer to your global minimum?
Okay, good. So that might be something people do, but instead we can control the, that's a good question. So we can control like our behavior as we get closer to the global minimum, or the minimum, hopefully, some good minimum, by decreasing the learning rate instead. Yeah, so actually the batch size and the learning rate are somewhat interchangeable. So we can slow down the algorithm as we get closer and closer to the minimum. So that's what's called a learning rate schedule. That's more advanced, I think, than I want to get into in these lectures. Yeah?
So if you're moving from one to the same batch, am I just selecting a subset of the data and not seeing all the data?
That's right. That's what makes it noisy. Yeah.
But then, so are they throwing out?
No, okay, so yeah, let me sketch out the whole process here. So the idea is we loop through the whole data set, batch by batch. Yeah. So yeah, so we divide the data into batches. We compute the gradient on a batch. We update the weights. And then we move to the next batch. And repeat. Okay? And when we go all the way through the data once, then we've seen the whole data set. And we give that process a name when we're training these things. So after we go through the entire data set, then we call that an epoch. Okay, and that's one training epoch. And to train these neural networks, typically we have to train them for many epochs, 10, 100, 1,000. Yeah, so we have to loop through the entire data set many times. And just one more technical thing, I guess. So when you're training these things, you don't want to see the data in the same order every time, just in case there's some false information that the fit is glomming onto. So at the end of an epoch, we typically shuffle the data. Okay. So that is, in a nutshell, how we train these neural networks. How am I doing on time? I'm supposed to stop at 5? Okay. Is it really 4:40? Okay, interesting. Yes? Is there a what?
Is there a rule of thumb for determining the batch size, the best batch size to use based on the size of the
Based on the size of the?
neural network?
Based on the size of the neural network. I'm not aware of any such rule of thumb. First of all, I should say that in high energy physics, we may not be so sophisticated compared to what the people whose lives depend on this are doing. So usually we just pick some nice number like 128 and don't think about it anymore. And that seems to work okay. But yeah, there might be rules of thumb. Yeah. Okay. Like nobody's going to die if we choose a slightly suboptimal learning rate or something. And also, like, we're trying to beat conventional things right now. So yeah, if there was a more mature subject that's been around for a while and people are really trying to get the last ounce out of it, then these issues would be more important. But the state of the field right now is there are just so many low-hanging fruits that it almost doesn't matter what you do, you're going to beat the previous state of the art. So it's a good place to be right now, I think. OK, good. So a couple more comments. Yeah, so in a nutshell, this is how we train neural networks. And lest you despair that this is all very technical, in fact, the computer science people have done us all a favor and written very compact packages. So you just have to enter in a few lines, press enter, and all this is handled under the hood. So in some sense, I didn't even have to tell you about any of this. But I guess it's good to know, I think, what is happening, a little bit about what's happening under the hood. OK, and just a few more things to know, I think. So somebody asked about an algorithm called Adam. So let's see, where should I? OK, actually, yeah. So good. So there's this whole question of how to choose the learning rate. And if you just fix the learning rate once and for all and don't change it, that goes by the name of stochastic or batch gradient descent. And in practice, what we actually use is something called, so in practice, people use fancier versions of this, of SGD. And two popular choices are called Adam and Eta delta. And in both of these, the AD stands for adaptive. OK, so people have come up with fancier versions of these SGD algorithms where they attempt to, one thing they attempt to do is to estimate at every step the optimal choice for the learning rate, sort of like you were suggesting. Like as we get closer to the minimum, we should maybe slow down and explore that in more detail. So there are ways to, that people have come up with is to try to estimate the best eta and adjust it as the training goes on. So that's, so yeah, in a nutshell, these are like SGD with adaptive learning rates. OK. And the last thing I want to tell you before we get to the physics example is how do we deal with overfitting? Yeah, how do we deal with overfitting? OK. So what's overfitting? You might worry that this is a problem because I've said these are networks that could have millions of parameters. And what if there are even more parameters than we have data? Because that can happen. So in classical machine learning or classical curve fitting, typically you would run into problems with overfitting when you have what are called overparameterized functions. OK. So one way to think about overfitting is to say that the fitting function memorizes the training data. And then it fails to generalize to new data. OK, so suppose my data looks like this. OK, what would you fit to that? Straight line. OK, but if I overfit, I might fit something like this. Right? Clearly overparameterized. Straight line has two parameters. Maybe to do this, I had to have a polynomial of 20 degree or something. So overparameterized, and it can memorize the training data, but not actually have learned anything, right? And then if I get new data, which is sort of drawn from the same distribution or the same process, right? This will be a very poor generalization to the new data, right? In between the data points that it's seen. Okay, so this is overfitting. And how do we deal with this or mitigate this with neural networks? Yep.
I think I know where you're going with this, but could you also solve this problem by adjusting the learning rate such that your parameters that you need to go to 0 go to 0?
it's a tough order. It's a tough business when the loss function is very complicated, non-convex. There's millions of parameters. Maybe in principle, yes, but in practice, I think probably not. Yeah. So, is there a question in the back? Yeah.
I'm not worried about. I'm worried about things like this, but also when you do fitting and you have more parameters than data points, there are flat directions in the chi-squared space. And the fit can't decide when it wanders around.
Might not converge on an optimal solution, right? Yeah. So I get So saying too much about like how neural networks get around the fact that they have so many parameters would take me too far afield. Again, there's some theory behind that, and it turns out so in fact that happens with the infinitely wide neural networks that I mentioned before. People have shown that when you take them infinitely wide, they actually reduce to something called a Gaussian process, which is like a free field theory. So in that case, although it has infinitely many parameters, there's some collective phenomena that takes over, and some emergent collective phenomena that takes over, and it turns out it doesn't have infinitely many parameters. It becomes like a continuous, it becomes sort of like a fluid at that point. So that's probably what's going on in general. But okay, so what we do to diagnose, so yeah, your problem is more like if we have too many parameters, we may get a suboptimal fit. It may not converge on a good solution. And whereas what this is saying is different. This problem is if I train it on the training data, my loss goes to 0. It looks like I'm doing great. And then I get new data that is supposed to be the same as the training data, and the loss is infinite, or just really bad. So the way we diagnose this problem, so the main tool for diagnosing and preventing overfitting, so for preventing overfitting, is something called the train val test split. Okay, so it's a very simple idea, but basically it means that it says that, well, if the issue is that we're worried about generalization to unseen data, then let's diagnose and mitigate this problem by only training on part of the data, and then using the rest of it to see if we're overfitting. Okay, and so yeah, what we do when we train these neural networks to make sure we're not overfitting. So again, this assumes that our data is IID, right? So then we divide our data into 3 chunks: the training set, the validation set, and the test set. Okay, and so these are all supposed to be statistically identical. And so we just train, so we do all the gradient updates here. Okay, and we will do things like plot metrics like the loss as a function of epoch. And we'll see on the training data, the loss will continue to decrease. Okay, and then we'll check. So we don't use the validation set to update any gradients, but we check the loss on the validation set. Okay, and we see maybe on the validation set, it's, oh God. So it's decreasing, and then maybe at some point it starts to do that. Well, these are not very different colors. So anyway, so on the validation set, we might see something like this. Okay, at some point it starts to increase. Then we're overfitting, right? And then what do we do to prevent the overfitting as best we can? We say, let's stop training at this point. So we say stop. Stop when the validation loss starts to increase. Okay, and finally, then we evaluate the performance of our network, of our algorithm on the test set. So we hold out the test set. So this is only after training for final evaluation. Okay. Good. So that's everything I wanted to say in general about how we train these neural networks. Yeah, questions?
Where does dropout fit into this?
Dropout. I have not told you about dropout. Dropout is another way to mitigate overfitting, which involves literally just deleting randomly nodes as you're training. The idea is that if it's overfitting, then it's sort of glommed onto certain features of the training data that are not real, and some of these connections are strengthened for not a good reason. So dropout deletes them randomly and keeps the, it's like another source of noise in some sense. So yeah, that's another technique, but you always do that, you always do this as the final check. Yeah, and you can do other things that also help. Yeah.
I just want to check something here. So when the check step, when you see your loss start to rise, I say at the stop, that tells me, okay, do this many epochs, and then so you go back into training, do that many epochs, and that's what I call my best fit, or?
Yeah, you don't have to go back. I mean, you're training. Here you just choose to stop. So you could save every epoch, basically. If you save the weights after every epoch, which is a smart thing to do in general, then you'll just pick this as your best epoch, and that's your best fit. Yeah. Yes?
So maybe you're going to talk about this in later lectures, but there's something that I'm generally curious about, which is how you given a data set, sometimes it's obvious for how you should package the data to feed it into the network. For example, if you have an image, each pixel you can put it as input node. But are there some examples where it's not obvious and there's some art to making a judicious choice?
Good. So in our example of top tagging, we will touch upon this, which is the problem or the question of data representations. Yeah. So how we package the data is not unique and is another choice. And depending on the problem, different representations can be more or less powerful. Yeah. And so that is a bit more of an art than a science. Yeah.
Is it for the image case, like for faces, is it obvious that you should just do one pixel as an input node and that's it? Or is there some other?
I think it's probably a good thing to, I mean, so given a data representation, then also we can design a network that leverages that representation. So with faces and pixels, or images and pixels, we do something called a convolutional neural network that the ML people came up with, which tries to learn local features in the spatial representation. And if your representation is a time series, then there are things that are optimized for learning sequence, long time correlations and things. So yeah, the choice of data representation informs sort of the choice of architecture. Is it obvious that we should be using pixels for images? I mean, in some sense, that's the lowest level representation of an image.
Yeah, I can't think of anything else.
Yeah, so that's what we want to do when we do this deep learning is choose the lowest level representation of our data, and the idea is then the algorithm can get the most out of that. Yeah. Yeah.
Thinking about real-world physics data, is there some way to check that the training, validation, and test sets, none of them have like some special feature that the others don't?
Well, yeah. I mean, usually these are okay. If this is top tagging that we're about to do, then these are generated with Pythia and MadGraph, so they're really IID, right? So then we just shuffle them, and we're fine. So in other situations, yeah, if there's any special features in one of these things that you can't get rid of just by shuffling them, then, I mean, if your data is too small, then you could be seeing you could be seeing fluctuations that are not real. Yeah. So with enough data, I think those kind of problems take care of themselves. Yeah. Okay, question.
Only tangentially related. When we assume our data is IID, if we're taking our data from an experiment that might have some like systematic uncertainty, does that influence this assumption of it using IID at all?
Well, if it's the LHC that I'm most familiar with, then I don't think there's any systematic uncertainties that go from event to event that we ever have to worry about. Yeah, there are systematic uncertainties, within an event. So like we couldn't take one part of the event and say that's IID from some other part of the event. But a given event, I think, happens pretty independently of every other event. Maybe there are some details I have to worry about with like the detector evolving with time, like it degrades over time or something. But whether that introduces a correlation between events, I don't think so. It's not like this event spoiled the detector for the next event, I think. Maybe some very energetic events could mess things up. But yeah, that's part of their cleanup. They probably don't want to consider such events. Yeah. That would just be my guess. Yeah. Good. OK. So I have 5 minutes. Looks like I will not get to the demo today, but I will hopefully be able to set up the problem of top tagging, and then we can start next time with the demo. I should say I posted 2 Colab notebooks to the Google Drive, and if you're not familiar with, how many of you have used a Jupyter notebook before? Oh, this is great. This is the modern era. Look at that. Wow. I first learned about it in 2018, and I used to use Mathematica a lot. And then I was like, wait, they designed something that's just like Mathematica. So it was perfect. OK, so you're all familiar with Google Colab then. So you can go to the Google Drive and just run these notebooks from beginning to end, and you can see sort of a fully worked out example, if you want, of top tagging. And if you are unmotivated to do that, we will go through it together at the beginning of next lecture. OK, so let's do our first application, boosted top tagging. OK, so here the problem is that we'd like to be able to distinguish top quarks, so a very energetic top quark. So the top has a mass of 175 GeV. So if its PT is much, much greater than its mass, it's highly boosted, okay? Which means that its decay product is typically highly collimated, right? And so a top will always decay pretty much to a B and a W quark. Sorry, a W boson. And the W boson will typically decay to 2 quarks. Okay. So a top, so this is called an all-hadronic top decay. There are other decay modes of the top, of course, but this is the interesting one for our purposes, because what it gives you is a very distinctive pattern of energy in this boosted, collimated, jet-like object. Okay, so the boosted top will give you what's called a fat jet. So a larger than usual jet, a larger cone than usual. And inside that fat jet will typically be 3 clusters of energy, okay, representing the B and these 2 quarks. Okay. And this is interesting to be able to pick out of the data. The bulk of the data is coming from gluons and, say, light quarks, which give me jets which don't have this substructure. Okay, they might give me a jet that just has a single bright pixel instead of 3. Okay? But I said the word pixel because I'm already thinking of them as images. But anyway, so they might give me 1 bright spot in the calorimeter and not 3. Okay, so and these are much more. So this is the QCD background. And QCD is this kind of QCD is much more numerous than this kind of QCD at the LHC. So it's an interesting problem. How do we distinguish between these 2 kinds of jets at the LHC? And if we can do that very effectively, we could look for interesting things. We can measure properties of top quarks, which are interesting in and of themselves. We can look for new physics that decays the top quarks or involves top quarks in some way. So there's lots of things we can do if we can pick out these boosted tops from the QCD background. OK, so this becomes a binary classification problem between a collection of jets. We want to separate the collection of jets into QCD jets versus boosted top jets. OK, so and the reason this is an interesting laboratory for playing around with these ML or neural network classifiers is that these boosted top jets have a lot of handles. Okay, there's a lot of features that we can think of that would be useful here. Okay, so it's a rich, is a richly featured problem. Yeah. Mm-hmm.
Since we could also directly take the LHC data for this stuff,
Yeah.
And they have their own classification of tops and non-tops, right?
Mhm.
And so, but they got it wrong sometimes, probably.
Mhm.
So there's some uncertainty. Could that also be the noise that we care to take into account for our stochastic gradient descent?
That's not the right kind of noise, I think. That's more like a error, like a mistake. Like that would prevent you from reaching optimality, I think. If you like trained on the wrong labels, probably. So that wouldn't be statistical noise. That would be more like systematic in some sense.
Okay.
But yeah.
Even if their noise or their mistagging is statistical?
It's probably not purely statistical. It's probably systematic, and like there's something about those jets that lead them to be mistagged. It's not a random thing. Okay, so yeah, this is a good setting for ML because the tops are richly featured and the simulations are pretty good. So we can do a lot of development playing around with methods and have confidence that we're not wasting our time using simulations that come with truth labels. Yeah, and then we can develop, or we, theorists, experimentalists, we can all develop cool, powerful methods, and they can go apply them to data and find that they work pretty well. So that's a empirical fact. Okay, good. And so the richly featured thing that I'm talking about is, well, there's a lot of handles because of this substructure here. And three of the most obvious ones are, if I plot the jet mass distribution, okay, the QCD background has a smooth continuum, right? But the tops have a nice peak at 175 GeV, right? So M top is a good feature. Sorry, not M top, M jet is a good feature. I can also go into the fat jet and say, give me the two clusters of energy, like force it to have three clusters of energy and say, give me the two that are closest to the W. And if I do that, so let me call that a W candidate. If I do that, then again, QCD will be roughly like this. And the tops will have a pretty nice peak at 80 GeV. Okay? And lastly, another classic feature. People have been working on top tagging for many years now. So another classic feature is a measure of how many subjets the fat jet has. And so, sorry, I ran out of space, but another feature here is something called N subjettiness, which counts, in some sense, it counts how many subjets this fat jet has. And if it has this 3 here versus 2, means if it has exactly 3 subjets, the N subjettiness peaks. And if it doesn't have exactly 3 subjets, it peaks somewhere else. So if you plot N subjettiness for tops versus QCD, you get a nice separation. Okay, so top tagging is a nice playground because we have these high-level features that can get us a pretty good top tagger. Okay, so this is like physics engineered, smart people came up with this stuff, got tenure. Okay, so that's like a good baseline, yeah? And then when the neural network comes and blows us out of the water, it's telling us something interesting. Okay, so that's where we'll start next time. Okay, thanks.